Hello, my name is Antoine Varagna. Welcome to this webinar. Today I will talk about ICCD detectors and their use for scientific research. And this webinar is aimed at being educational and presenting some of the basic functionalities, components of this type of cameras. We'll cover some of the key aspects of ICCDs for low light level detection, as well as their ability to isolate very accurately in time some very specific events. We look more in detail how image intensifier based detectors are built, some of the key components and considerations when selecting the different options for this type of detectors. We'll talk about the gating aspect of ICCDs, the principle of gating and the different timing considerations. We'll talk eventually about sensitivity and dynamic range for this type of cameras and some of the noise source considerations. And finally, we look at some of the applications for science for this type of technology. So first of all, ICCDs are based on a particular element called image intensifier. And image intensifier are used for night vision technology, for likes of night vision goggles, as illustrated here. And they have the ability to detect extremely low light levels down to single photon. They compete since about 2001 with another type of sensor technology called electron multiplying CCDs or EMCCDs, but have the same type of ability to detect very low photon fluxes down to single photon, for example, for photon counting. The primary difference here is when sub-millisecond shuttering is not needed, EMCCDs are perfectly suitable for this type of detection. ICCD gating is really the differentiator here. So ICCD gating enables some very high time resolution experiments. Image intensifier and specifically their element called photocathode can be gated, shuttered at sub-nanosecond levels to be able to isolate a snapshot of a phenomena in time. The reasons to do gating is, for example, if you want to shutter signal or unwanted excitation source on your experiment. Some experiments are laser-induced, for example, laser-induced fluorescence, laser-induced breakdown spectroscopy. You don't want to see the initial laser excitation, you want to see the information just after this laser, and this information can be available in a very, very short time frames, nanoseconds, microseconds, and so on. Another use for ICCD gating is the ability to take a number of snapshots of a transient phenomena and being able to build a movie, if you want, of a phenomena, like illustrated at the bottom of the page here with a plasma bullet. This little video was made of individual images, individual snapshots of the plasma bullets as it propagates after initiation. In the context of 2D detectors, ICCD are capable of time resolutions down to the nanosecond level, but can cover as well some microsecond time resolution needs as well. CCDs are traditionally quite slow scan CCDs we talk about, and the type of shutter you can use for these cameras are extremely slow. They're in a few hertz regime, especially for imaging applications. EMCCDs and CMOS or scientific CMOS cameras are capable of faster acquisition rate, faster frame rates, but it's still in the millisecond to hundreds of microseconds time regime. On the other end of the scale, you have street cameras that are modules that are capable of doing picoseconds type of resolution. So ICCD sits between street cameras and the CCD technology, being able to get down to nanosecond level time resolution. Let's look a little bit more in detail some of the key components of ICCDs. So this is a little diagram of the optomechanical arrangement of an ICCD. And the incoming photons are coming from the experiment at different wavelengths and are absorbed and converted to photoelectrons to be detected eventually by the sensor. So first of all, the photons traverse an input window, which is effectively a window used as a substrate for the photocathode of the image intensifier, and the window is as well used to seal the image intensifier because the inside of the intensifier is under vacuum. The photocathode, the crystal, is deposited on the input window, and the photocathode is a key element here because it can convert the photons from the experiments to photoelectrons. And this photocathode is the element that is gettable, that will provide a very fast shuttering. The next element in the chain here is an element called microchannel plate, or MCP, and this is the part of the intensifier that does the intensification. And this intensification is based on impact ionization, generating secondary electrons to amplify an initial single photoelectron coming from a photocathode. The phosphor is the next element in the chain here, and the phosphor basically converts the photoelectron signal from the MCP to visible photons, and these visible photons can be detected by a sensor. These photons can be channeled to the sensor through different means. The main ones are fiber optic plates to channel the photons straight through to the detector, or a lens coupling. Finally, the last element here is the sensor, 2D sensor, and typically a CCD, an SCMOS. As well, you can find some interline CCDs or even EMCCDs to do the collection of the image or the spectrum. The input window defines the lowest detectable wavelength of the image intensifier, and there are a couple of different technologies for image intensifier, basically the type of material they're made of. The generation 2, so-called generation 2 photocathodes are deposited typically on silica. So if you look at the graph at the bottom here, 50% transmission efficiency is a cutoff around 160 nanometer. For some specific applications, these Gen 2 photocathodes can be deposited on magnesium fluoride, and that extends the response down to 125 nanometer roughly. Generation 3 photocathodes are only available on glass, and that's because there's a need to match the thermal expansion of this type of photocathodes with a substrate, and the only substrate that's matching Gen 3 photocathodes thermal expansion is glass. One of the downside of glass is that it cuts off UV, so Gen 3 intensifiers using glass window cannot really detect below 300-350 nanometer. There are different types of photocathodes, as I mentioned. Generation 2 photocathodes are really broadband photocathodes, detecting potentially from VUV to near infrared. They have fairly moderate peak quantum efficiency, about 25%, and they're made of multi-alkali elements. They are very resistive and not very easy to gate, to shutter very, very quickly. To achieve nanosecond gating, these photocathodes typically have to have an additional element deposited on them, and that's an underlay, a metallic underlay, typically nickel. And this nickel allows to improve the conductivity of a photocathode, but because you have an additional optical element in the optical path, it does have a negative impact on the quantum efficiency. That use of metallic underlay allows the photocathode to be gated down to a few hundreds of picoseconds in some scenarios. Generation 3 photocathodes are made of gallium arsenide, and as I mentioned before, they're only deposited on glass, so they don't have any UV response. However, they don't need an underlay to be gated down to hundreds of picoseconds. Therefore, they have pretty good maximum quantum efficiency, up to 50%. There's a third type of camera and intensifiers based on InGaAs material. And in-gas material will provide detection up to 1.1 micron and is really focused on detection in the infrared. The maximum quantum efficiency of these photocathodes, however, is quite low, about 5%. Depending on the recipe of the different elements and the mix of the different elements in the photocathode, the response of the photocathode can be tweaked a little bit. With Gen 2, some of the Gen 2s can be tweaked more to have more response in the near infrared. That would be the red curve here. Some photocathodes would be tweaked to have better quantum efficiency in the UV. Just to illustrate the impact of the underlay we discussed for generation 2 to be able to do fast gating. Here is an example of a what you would call a full underlay, which is a blue line, which would be a fully coded photocathode, and a grid underlay, which leaves gaps between the different elements of the underlay to balance the ability to fast gate the photocathode, as well as not absorbing too many photons and reducing the quantum efficiency of the photocathode. So underlays do have an impact, a positive impact on how fast you can gate the photocathode, but it has a negative impact on the quantum efficiency. Gen 3 photocathodes, as I mentioned, have no or barely any UV response below 300 nanometer. However, they do have a peak quantum efficiency up to 50%, which make them pretty useful if you're doing the likes of photon counting, having a better absorption probability or detection probability of these single photon events. The next element is a microchannel plate, or MCP. And MCPs are the gain chain, the amplification chain of image intensifiers. And the main role of the MCP is to overcome the sensor noise floor, to extract a very, very faint signal from the experiment, extract them from the noise floor of the camera. And typically, the source of noise that is overcome is the readout noise of the camera, a CCD or a CMOS. The MCP, when toggled to the maximum, would allow detection of single photons events. And sometimes a dual MCP is used to really amplify the contribution of single photons well above the noise floor of the camera to ensure accurate detection of these single photon events. So microchannel plates are made of all of these little different channels here, and photoelectrons, incoming photoelectrons to the MCP hit the wall of the channels and can create a secondary photoelectron. There is a voltage difference between the input of the MCP and the output of the MCP, creating an electric field, and the photoelectrons are accelerated and by impact ionization multiply and create a cloud of photoelectron. That's the principle of the amplification. The graph on the right hand side gives an idea of the impact of gain on the signal to noise ratio achievable, and here you can see with a small gain of 1, the useful signal is buried into the noise floor of the sensor. As the gain is increased, the useful signal is extracted above the noise floor of the sensor. Phosphors are the next element in the optical chain, and phosphors are used to convert the photoelectron signal amplified from the MCP back into visible light, typically in the green. And in the green because that's where CCDs and CMOS are the most sensitive. There are different types of phosphors available, and the selection of phosphor depends on primarily the frame rate of the acquisition. So for acquisition using very low frame rates, the main phosphor type used is called P43. And P43 are phosphors that have a decay time to 10% of about 2 milliseconds. So decay time means when the phosphors are first excited by the cloud of photoelectrons coming from the MCP, it takes 2 milliseconds for the effectively the intensity of a signal to come down to about 10% of the initial intensity when phosphor was first excited. If acquisition rates are greater than 300 Hz, there's a potential for corruption between consecutive frames. So for example, the first frame, the contribution of the first frame wouldn't disappear completely by the time the second acquisition is started. So you might have a unwanted background or lag from the first image into the second image that can reduce the dynamic range and the accuracy of the measurements. In that case, a faster phosphor like a P46 can be used, and P46 have decay time much shorter, about 200 to 400 nanoseconds. However, they do have a lower efficiency at converting photoelectrons into visible photons. They're about 3 times less efficient than a P43, and as well have a very small difference in resolution limit compared to P43. So now the phosphor has converted the photoelectrons into visible light. This visible light has to be channeled to the sensor for detection. There are a couple of methods to channel this light to the detector. The first one is using fiber optic plates, little structures, individual structures, like you can see the little honeycombs here, and mechanically coupled to the image intensifier and the sensor. The second method is to use a lens coupling to relay the light from the back of the phosphor to the sensor. So fiber optic plates have some pros and cons. Fiber optic plate approach allow to better channel the light down to the sensor and avoid any scattering. So this approach is typically better for signal collection and throughput. Also, the fact that they are mechanically coupled very close to each other between the image intensifier and the sensor makes the design of the camera very compact. You can see that these structures on the fiber optic sometimes can be imaged, and they contribute to a very low intensity background on the image. Now this background can be subtracted, taking an image in darkness and subtracting it from the useful image. The lens coupling approach typically gives better spatial resolution. However, image intensifier do blur the signal, do have a spatial resolution limit, and typically the spatial resolution limit of the intensifier is the bottleneck. So there are very small gain in having a lens coupling in terms of spatial resolution with ICCDs. Lens coupling, however, suffers from potentially distortion and vignetting if the lenses are not properly optimized. And also, to fit the lenses, fit all the optical elements, the distance between the back of the phosphor and the sensor has to be increased, and that creates a bigger footprint for the camera. There are two main types of sensors used in ICCD, which I will discuss. One is CCD, the other is scientific CMOS or SCMOS. With CCDs, a photon signal is collected by a pixel, and the signal from this pixel is read through a readout register. This readout is done 1 pixel at a time and can be very slow. The faster you want to read these pixels, the more read noise you introduce. For CMOS, the amplification and the digitization is done at pixel level. So a full line of a pixel can be read simultaneously, and CMOS through this architecture can yield faster acquisition rates compared to CCDs. CCDs or ICCD based on CCDs are perfectly suitable for the likes of slow scan spectroscopy and fast frame rate spectroscopy up to kilohertz. When it comes to imaging, CCDs have limitations and typically can achieve few hertz frame rates imaging or multi-track spectroscopy. Multi-track spectroscopy being the ability to image through a spectrograph multiple fiber optic contributions on top of each other along the slit and taking a snapshot of all these contributions at the same time. Then the image is processed to extract each contribution from the image. CMOS, on the other hand, are extremely well suited for the very fast imaging frame rates up to multi-kilohertz, and also maintaining a high dynamic range. I will cover that in the next few slides. They're also very suitable for fast multi-track spectroscopy. Let's talk a little bit about now gating of a photocathode and triggering. So in an image intensifier, the MCP voltage shown at the bottom here is held at a fixed value, here plus 150 volts. The photocathode voltage is however toggled to effectively reverse the direction of the electric field between the photocathode and the MCP. And this photocathode is basically toggled between 0 volt and 200 volt here. So you can see that depending on whether it's 0 volt or 200 volt, the electric field would go toward the left-hand side, toward the MCP, or toward the right-hand side. So gating is achieved by switching the direction of this electric field and basically allowing photoelectrons generated at the photocathode to propagate towards the microchannel plate or not. If the electric field allows the photoelectrons to be reaching the microchannel plate, they will be detected. When the photocathode is off, the photoelectrons are not making their way to the MCP. So gating image intensifier has some limitations. So photocathodes are crystals and they have a finite conductivity. They act as RCL circuits if you want. And if you apply a high voltage pulse to these elements, it takes time for the electrical pulse to propagate from the edge of the photocathode to the center of the photocathode. And this difference of time influence when the photocathode edges are effectively open and when the center of the photocathode is effectively open. And there is a delay, and this delay is called irising time. And this irising time is typically a few hundreds of picoseconds for the fastest gated intensifiers. In the ultraviolet, even if the photocathode is off and the electric field repels the photoelectrons away from the MCP, higher energy UV photons can sometimes go through the photocathode and not be absorbed and reach the MCP. And sometimes they have high enough energy to generate photoelectrons. Now remember that only the photocathode has been toggled. The MCP is always on, always amplified whatever comes its way. So a leaked UV photon reaching the MCP, creating an electron, a photoelectron, this photoelectron will be amplified and will be detected by the sensor. There's nothing to stop it. And that leakage will contribute to lowering the on-off ratio capability of the intensifier. So if you look at the graph at the bottom right here, you can see that the on-off ratio in the UV at 200 nanometer, if you only get the photocathode, will get you about 10 to the power 4 on-off ratio or rejection. If you were to gate simultaneously the MCP, you would then prevent the amplification of these unwanted photoelectrons. So that's a mode on the outdoor camera called IntelliGate, that's shown on the graph here. And simultaneously gating the MCP and the photocathode gets you back from an on-off ratio of about 10 to the power 4, 10 to the power 5 to about 10 to the power 8, 10 to the power 9. The MCP gating is therefore useful to increase the shuttering of radiations in the UV, where you have a lot of scattered UV photons. Let's look at some of the typical timing diagrams for ICCDs. And let's focus on the scenario where the camera is used as a master and is internally triggered. So the graph here shows at the bottom left, at the top left, an internal camera trigger starting the experiment. And the start of the experiment would basically mean that the sensor starts to expose. The photocathode gate can then be delayed very accurately to match when an event, shown at the bottom here, will occur. And since the camera is the master in that scenario, the camera can output a trigger that would start the event. And this trigger can be set at a particular time from the internal camera trigger, and that is the delta 2 timing represented here. So the event is triggered and the photocathode can be very accurately positioned from this original internal camera trigger to capture the event in time, and only this event in time, and reject everything else around it. The second scenario here is when the camera is a slave and you have an event, and this event, for example a laser, can be triggering the detector, or you can have a separate master trigger that would trigger the camera and the experiment simultaneously. So imagine the scenario where the event generates an external trigger to the camera. The external trigger is received by the camera, and it takes a little bit of time, called the insertion delay, to actually get the sensor to expose. Then after the sensor starts to expose, you can open the photocathode to look at a particular event. You can see in this scenario that the event that is captured by the photocathode is not the event that triggered the camera. That's because the propagation delay and the time to get the photocathode ready is too long. So in that scenario, you use one event to trigger the camera to effectively capture the signal from the secondary event, the next event, sorry. If you have a master trigger that will trigger the event and the camera separately, then you can use the first external trigger, start the exposure of a sensor, position the photocathode accurately in time from this master external trigger to capture the actual event triggered by the master trigger. Okay, let's talk now about sensitivity and dynamic range for ICCDs. So when looking at specifically sensors like CCD or CMOS, there are a number of sources of noises to consider. The first one is shot noise. It's a source of noise you can't really do anything about. It's linked to the quantum efficiency of the sensor, and it's linked to the intensity or the amount of photons hitting the detector in the first place. The second type of noise that is important for sensors is a readout noise, and is usually the detection limits for the majority of sensors like CCDs and CMOS. A third source of noise is a dark noise. The dark noise is basically a representation of thermally generated noise by the sensor. That's why for scientific applications, sensors are cooled down to remove the contribution of this dark noise. Another type of noise that can be found on CCDs or CMOS or interline or EMCCDs are clocking induced discharge. For CMOS and CCDs, these are quite negligible. So that's the sensor side of things. The primary noise to tackle in ICCDs is the readout noise. So to tackle or to overcome this read noise floor, that's where the MCP gain comes into play. You take a very faint signal, amplify it before well above the read noise floor before it reaches the sensor where the read noise contribution is added. As I mentioned, the dark noise can be greatly minimized with good cooling, and or the acquisition rates are so fast that the dark noise, which is time dependent, is not contributing enough to impact the signal to noise ratio or the detection level. CIC noise is also very, very negligible in CCDs and CMOS, and is typically not the bottleneck for any of the detection. So again, you can see the graph here showing the extraction of a signal above the noise floor of a camera, by applying some gain. An example here of how powerful the MCP gain is in relation to extracting a single photon information from a noise floor is these quantum entanglement images, which are accumulation of single photon events detecting very, very high gain and accumulated over an amount of time. So when it comes to ICCDs as a whole, we've talked about the different contribution of noise from the sensors, the photon shot noise, the read noise, the dark noise, CIC, and so on and so on. Some transient pattern noise can be seen as well in some technologies. This can be corrected through FPGAs or tackled in separate ways. At the photocathode, there are a couple of noises to consider. Photon shot noise from the photon signal from experiment, as well as another source of noise called equivalent background illumination, or EBI. I will come back to that noise in the next slide. The MCP carries a number of noise as well, noise contributions. The first one is the shot noise associated with a photoelectron cloud coming from the photocathode and reaching the MCP. And then MCP amplification relies on a phenomena that's not guaranteed. The generation of secondary photoelectron is a statistical process, and there's a certain probability of generating secondary electron or not. So there is a certain noise called amplification noise factor that is associated with this type of impact ionization amplification. This is the same principle than EMCCD amplifications, and EMCCDs as well have an amplification noise factor. The phosphor as well sees the photoelectron cloud amplified coming from the MCP, and there is a shot noise as well associated to it. So there are a lot of different noise sources. We've seen that from a sensor point of view, the main one is a readout noise. However, applying MCP gain would overcome to an extent this readout noise. The primary source of noise and limitation of sensitivity of ICCDs besides shot noise is EBI. So EBI is a spontaneous emission of photoelectrons from a photocathode through thermal excitation, and that's not from photoabsorption. So basically, if you were to leave the camera in darkness and put the gain very high and take acquisition times of maybe a second as shown above, you will see all these little speckly noise that are single EBI events being amplified by the MCP, making its way to the sensor and being detected. And these events look exactly like single photon events. So if you're doing photon counting application or single photons, this EBI noise will be a factor impacting the statistics and the quality of a single photon detection, if you want. So alongside shot noise, EBI is the ultimate sensitivity limitation in ICCDs. There are certain ways to improve the signal-to-noise ratio in ICCDs. One of them is described here and called integrate on chip. So if you look at the graph at the very bottom of the screen here, CCD exposures can be typically milliseconds. And during the CCD exposure, you would open the photocathode, like a normal photocathode gating mode would be one gate. And the rest of the time is basically accumulating noise from a camera or from a sensor, and not making the full use of potentially over useful signal being generated by the experiment. So if you look at the very top of the graph here, you have, for example, a source, a laser, high repetition rate laser, that will generate useful contribution of signals at a certain frequency. But in a normal photocathode gating mode, you only capture one of these contribution per CCD exposure. There's a lot of useful information wasted. So by opening the photocathode in sync with the laser, for example here, a number of times during the CCD exposure, you can effectively accumulate on chip multiple contributions of the experiments and then read out one CCD exposure. And the impact of this approach is shown on the insert on the right-hand side here. A single accumulation, the signal cannot be seen above the noise floor. Then doing a number of accumulations, a number of gate opening during the CCD exposure or the sensor exposure allows to extract the signal from noise floor and give extremely good signal to noise ratio. Let's talk about dynamic range now. So when it comes to ICCDs and overcoming the noise floor, the greater the read noise floor is, the higher the MCP gain has to be to overcome this noise floor. The higher the MCP gain, the lower the accessible dynamic range for the camera is. So in other words, if the read noise is very high, you need to apply higher MCP gain, and applying higher MCP gain will impact the dynamic range of through an acquisition. So the little table at the bottom summarizes the read noise performance of 3 different types of sensors typically used on ICCDs. The first one is a CMOS sensor. The second one is an interline sensor. The third one is an EMCCD sensor. And when these are operated at their fastest for demanding transient sampling of phenomena, the read noise of this technology will vary greatly. So for CMOS technology, which is a technology specifically designed for low noise, low readout noise, you can see that you can get very high frame rates and a low pixel read noise, about 5 electrons in that case here. Looking at other technologies operated at the fastest frame rates, you can see that there are order of magnitude higher read noise than CMOS. That means there's going to be a need for more MCP gain to be applied to these technologies than the CMOS based technology to overcome the readout noise. So let's do some maths here, not too complicated. So to really access a good signal to noise ratio, you can say as a rule of thumb that you need to apply 6 times the value of the read noise in terms of gain. So for example, if your readout noise is 5 electrons, like the case for the CMOS based camera, you need to apply about 31 times gain to overcome really this noise floor and give good signal to noise ratio. For the interline camera or the EMCCD based cameras, you can see that there are again order of magnitude higher MCP gains required to overcome the noise floor. Now, you're limited by the pixel well depth, the ability of a pixel to hold charges. They have each pixel have a certain capacity. So if you now ratio this pixel well depth capacity to the gain used to overcome the noise floor, that gives you an indication of your true dynamic range for the camera. And in the case of CMOS, because the read noise is so much lower to start with, and there's no need to use very high MCP gain, the dynamic range can be extremely good and much higher than the other type of sensor technologies. And that's useful whenever you're dealing with very fast acquisition rates. You can not only acquire these images at these fast rates, but as well have images with high dynamic range and high contrast as well. So that's the power of SCMOS based ICCDs. Now let's focus on a few application examples for these ICCDs in science. So one application is laser-induced breakdown spectroscopy, which is basically a technique used to determine atomic composition of samples, and it's based on laser ablation. So when a pulse laser interacts with a material, a plasma is created, and the plasma goes through different phases. And you can see these different phases here: continuum, ionic, atomic, and molecular information in time as the plasma cools down. In the early stages of this plasma, the emission from the plasma is really broad. It's called a branch-stratum continuum. And there's not really any useful spectral information, very narrow feature in the spectrum to determine accurately the composition of a sample. As you look further away in time, further away from the laser, you start to see some very nice spectral features appearing that are associated with a particular element of a sample. And if you continue in time, you then are past the broad continuum phase of the plasma, and you are in a relaxation period of the plasma, a cooling down period, and that gives you the useful atomic information. So in laser-induced breakdown spectroscopy, you don't want to see or detect the initial laser. You don't want to see the initial continuum, which happened a few hundreds of nanoseconds. And you want to isolate very accurately in time these microsecond to tens of microsecond information after the initial laser pulse. That's where the useful atomic information is. ICCDs are the only type of detectors that can provide this timing, being able to delay a few hundred nanoseconds the acquisition of useful signal after an event and only look at a few microseconds. A practical example of application for LIBS is the use for material analysis. So on this example here, it's a team at Allahabad University in India, and LIBS was used as a technique to determine the composition of meteorites, the so-called Darganford meteorite back a few years ago that landed in India. And the analysis of the composition of this meteorite can tell a lot of things about where they come from, and maybe some information about the formation of the universe as well. So this particular technique was applied with an Echelle spectrograph to give very broadband spectral coverage and very good high spectral resolution. And in that case, that was an underarm Echelle used with an I-star ICCD to do this acquisition. Another example of the use of ICCDs is the remote detection of chemical threats. So on the top right-hand side, you have a powder, and it could be anything from explosive to maybe sugar or flour and things like that. It would be very dangerous to have an operator collecting the sample on site and bringing back to the lab for analysis. So some techniques have been developed over the years to allow remote probing of a sample non-invasively to protect operators and be able to determine very accurately the nature or the type of sample we're dealing with. So to do that, in that particular case here, using a technique, an optical spectroscopy technique called Raman spectroscopy in the UV, and basically a laser is shown onto a target at a distance, and the Raman effect takes place on this target, and the Raman signal collected back from a target gives a chemical signature of the sample. And this chemical signature can be matched against a library of known chemical signatures, for example, of explosives, as shown on the graphs here. You can see that RDX, TNT, PETN have unique chemical signatures, and if an unknown sample have a very similar chemical signature, you have a high probability of determining what this particular sample is. In that case, the ICCD is used because the Raman signal is very weak, and the Raman signal is only present when the laser, the pulse laser, is on, and the pulse laser can be only a few nanoseconds. So you have only a small nanosecond time frame during which the useful signal is generated, but then you have potential disruptions from the sun and scatter lights, because this type of detection is done outdoor. So the ICCD can be used to really look at a very small nanosecond time window during which the Raman signal can be collected and rejects all of the unwanted sunlight and other scatter light that could hamper the useful signal information. Another type of applications for ICCDs is plasma science, and specifically transient plasma science. So here are a few examples of different type of plasmas. On the top left here is a pulsed electric barrier discharge, and the team at Greifswald University looked at the influence of the gas flow rate on the stability of this dielectric barrier discharge. The second one on the right hand side looks at the surface electric discharge in atmospheric air. It's a snapshot of these streamers, if you want, taken at University of Notre Dame. The last one, which we've seen on the previous slide here, is a kinetic of a plasma bullet acquired at University of York with one of the SCMOS technology, and basically being able to sample in time over many iterations the behavior of the plasma and reconstructing that through a little movie like that. Another type of science that can be done with ICCDs is quantum science, and specifically quantum entanglement. So quantum entanglement is what Einstein described as a spooky action at distance. Basically, two photons become very inextricably linked, and whatever happened to one influences the behavior of the other one, although they might be very, very, very far apart. In that particular case, the team at University of Vienna accumulated a number of single photon events to create these images that you can see on the left hand side, but they also play on the trigger photon polarization to create different type of spread of the single photons during a single exposure of the camera. And they can use the ICCD gate to isolate a single photon contribution exactly when it reaches the detector and remove some of the unwanted scattered light or ambient light that would destroy the statistics of these experiments. Another type of applications where ICCD are used is the field of fluid dynamics and combustion. So this is an example of an ICCD used alongside a reactor, and the team here is looking at the flame generated inside the reactor and the flame interaction with the wall to replicate flame wall interaction in diesel engines. And basically the team is looking at time sequence, very accurate time sequence of the profile of the flame when it interacts with this wall, and probing particular species generated during the combustion, if you want, isolated these species, exciting them with a laser to do the likes of planar laser induced fluorescence type of imaging to create this contour of the flames at different time. And that concludes this presentation. Thank you very much for your attention. If you require any more information about this camera, please do not hesitate to contact your local ANDR representative. We'll be more than happy to provide additional information on these cameras. Thank you and goodbye.